Hi folks, this is your Professor Ken Schwitkus talking about the outer planets now. We have several various versions, well not versions, but parts to this one. First part is to talk about the structure of the planets. And so here we have the four of them named out, Jupiter, Saturn, Uranus, and Neptune, in their order from the Sun. Here's pictures of them. And some little details about each one. Jupiter over here, Neptune on the other end, and we have the little teeny Earth here to give you an indication of size. Okay, Jupiter, if I recall correctly, is about 300 times the size of the Earth, and Neptune and Uranus are about 15 times. Saturn is somewhere in the middle at 95. So, and then the other thing that's kind of interesting is if you want to decide to memorize the distances from the Sun, you can do that. You can go for Jupiter is 5, Saturn is 10, Uranus is 20, and then Neptune is 30. So those are nice, easy round numbers. And as I keep on saying in astronomy, if we know things to 10%, we're doing pretty well. The densities, though, are very interesting in comparison to the Earth. Remember, the Earth is about 5.5, maybe a little bit more in grams per cc, remembering that water has a density of 1 gram per cc. And you see that these planets are really pretty fluffy in comparison to even water. They're very fluffy in comparison to the planets we talked about last week. So here are the things that perhaps you would want to think about. You've probably heard that Jupiter is a failed star, and hopefully we'll set your mind at ease on that. It really isn't. Especially when we talk about the Sun, and if you take the other class, when we talk about the evolution of stars, you'll find out that Jupiter is about 100 times smaller in mass than is necessary for light to turn on. Some of the other interesting things that we're going to be talking about in this section have to do with not only the composition of the planets, but in the next time we'll talk about their atmospheres, relating those atmospheres to what we see on the Earth and the terrestrial planets. And we'll talk about the moons and the rings. Those things are very, very, impressive. Especially in terms of Saturn's rings, but also very interesting in their own regard. All right, well, the composition goes, is what you would expect given our solar system creation story. We figure that all of these planets have rocky cores, but the overall composition is mostly hydrogen and helium for Saturn, and for Uranus and Neptune it is compounds of hydrogen and helium. Now if you look at the overall density of these guys, as we saw before, then Jupiter and Saturn, all these are rather fluffy, and you could see if you had a bathtub big enough, then Saturn would float. It's sort of similar for these two guys, Jupiter and Uranus. If you put them on the ocean, they may float. Okay, we're about, for oceans and even for the very saline lakes, those densities are about 1.35 in grams per cc. And if the entity has less density than the thing that it's floating in, then you'll be floating. Now, one of the previous chart also, asked the question, why is it that Saturn and Jupiter, even though they are so much different in mass, after all, look at this, this is 300 times the mass of the Earth, and this was only 100 times, then why in the world are these two planets about the same size? And it all has to do with the fact that Jupiter has so much more mass and it is compressing still. So the compression effect makes the planet denser, even though it's made of the same stuff. And in fact, if we got to something like 3 times the mass of Jupiter, then the size would be about the same as Jupiter. And in fact, we could see at 10 times the mass of Jupiter that we would have the same size as Jupiter. Very interesting indeed. Now, the other interesting thing that happens with both Jupiter and Saturn is, since they are big fluff balls, and this is also true with the Sun, is that they sort of get pushed down from their axial rotation. So I don't know why it's doing this, but the point is that if you have rotation about the center axis here, so it's rotating around like this, that this region sort of bowls out and these regions compress in. So we have a little animation here to show it to you. It's kind of on the boring side, but here we go. And as I increase the rotation, then you see that the poles get closer together and that the diameter of the planet around the center region expands. So here this is much shorter than this region here, and if we can slow it down to slow rotation, you see it's about the same. Okay. Right, now the interiors of the Jovian planets, we basically think that they were created the same way as the terrestrial planets. We're going to have planetary differentiation at some level. We're going to have very, very dense materials in the center, and it's going to become lighter as we get further away. And indeed, that's what happens. In the core, we have rocks and metals and hydrogen compounds. But then from here on out, and notice that this is about the size of the Earth, but it's much more dense. As it says, it's 10 times more dense. And then as I go out from here, this is metallic hydrogen. Remember, hydrogen is a gas. And here, what are we doing with a hydrogen as a metal? Well, what's going on is there's so much mass pushing down on this thing that we now have pushed these gas molecules so close together that they are forming a metal. Because of this metallic structure, then the electrons are free to move around, and thereby giving us the source of a really strong magnetic field. All right, and then further out we have liquid hydrogen, and then we have gaseous hydrogens, and then we have the cloud tops, which we see most frequently. The Jovian planet interiors, basically Saturn and Jupiter, are very similar, just a little bit differences in how much metallic hydrogen they have. So Jupiter gobbled up more stuff than Saturn was able to, and that's basically the differences. And what we see with Uranus and Neptune is they don't have the metallic hydrogen, but they have the other things as well. So, the sizes are such that they were not able to capture as much hydrogen, the original solar nebula, as Saturn and Jupiter were, but they gained the ices and they gained some molecular hydrogen. Notice the size here, we're going out to 26, and as far as distances out, from the Earth, right? This is 8 times the radius of the Earth, 16 times, and we go out to 71 for Jupiter. But the idea is that, these guys, if you recall, they're about 15 times the mass of the Earth. This is about 100, and this is about 300. Now, we do have a lot of heat emanating from these Jovian planets. We have an idea of what's causing that heat to be emitted from Jupiter and Saturn, and Neptune is a mystery. While on the other hand, we don't really know what's going on with Uranus at all. So all 3 of these planets are emitting twice as much energy as they receive from the Sun. Jupiter is still believed to be contracting, and so when you contract, then the potential energy associated with gravity gets changed into kinetic energy. that kinetic energy increases the temperature, and that temperature convects out to the outside surface. And for Saturn, we figure that we have differentiation continuing on. And so differentiation is going to cause a change in density, and essentially, we're going to have a temperature increase again. So in a sense, that's what's going on with the internal heat sources, which is kind of surprising in its own regard. Okay, we'll get to the next section in a moment.